Hello guys, in this part we will talk about the most important effects of transmission lines, which is reflection. First of all, let's ask a question. Why reflection does happen in transmission lines? We knew from previous parts transmission lines, or for more specific, two conductor transmission lines. When in two conductor transmission lines, when an electrical signal with high frequency is applied, these two conductor or this transmission line will be look like sequence of RLC circuits. So this transmission line will have resistance part attenuate or resist the following of the current or the following of the power or energy, and reactance and also the conductance. Okay, the conductance here will resist this following of energy, and also there will be reactance part represented by the inductance and the capacitance effects or behavior in these two conductor, and these or this part will behave all or will work to store energy, okay, as a electric field or as a magnetic field inside them. Okay, so if such a transmission line terminated if such a transmission line is terminated with a specific or with an arbitrary load with a specific impedance, let's call it Z load, okay, and this impedance of this load is could be antenna, for example, this could be any other component like filter, like amplifier, okay, anyone. So the impedance of this load is different with the characteristic impedance of the transmission line itself. So there will be difference between the power which is propagated or traveled, okay, inside the transmission line or through the transmission line, and the power or the energy will be dropped or delivered by the load. Okay, that's because here the concepted power here by the attenuation or by the resistance and conductance is different from the concepted power at the load, and also the stored part is different, okay, about the stored part in the load. Okay, so because the mismatch between the impedance of the load and the characteristic impedance of the transmission line, so there will be difference between, or there will be amount of the power, okay, different between them, between the power which traveled and power which will be delivered. Okay, in other words, not all the power which sent by the generator through the transmission line, now not all this power, okay, will be delivered to the load, or maybe nothing from this power will be delivered to the load. Okay, and this is very big a problem. So now this power which will not be delivered to the load, this power will be propagated in opposite direction, okay, opposite direction from the travel direction, and we call this power, which will propagate in the opposite direction, by reflected power. Okay, so along the transmission line there are two of the power which will propagate in two direction. Okay, traveled one or propagation one from generator to the load, and reflected one, okay, reflected from the load towards the generator. Now the difference between the two will be in the amount and in the phase. So maybe all the power which will be propagated will not be delivered to the load, and all the power will be reflected. So there is nothing will be received by the load. All the power will be reflected from the load to the generator along the transmission line. Or sometimes part of the power will be received or delivered to the load, and other part will be reflected because the mismatching between the characteristic impedance and the load impedance. Okay, so along the transmission line, as we said, if we need to measure the voltage or the current at any position at any point along the transmission line, according to that, along the transmission line, if we need to measure the voltage, okay, or the current on any point across the transmission line, so the voltage which will be measured or the current that will be measured represented the superimposition between the travel voltage plus or superimposed with the reflected voltage. Okay, and same for the current, the difference between the travel to the reflected. Okay, so according to that, the total voltage now along the transmission line, of course its function to the position, to the z, okay, represent the total or the traveled voltage superimposed with the reflected one, and also the current, the traveled superimposed with the reflected one. Okay, so the voltage and the current will be oscillated along the transmission line depending on the position. Okay, and same for this is the for the impedance, the ratio between them. Okay, so now if any transmission line, two-conductor transmission line, is connected with a high frequency generator and terminated by an arbitrary load, so now we have a system, okay, with a new impedance represent the ratio between the voltage along the transmission line or the voltage at any point on this transmission line to the current which is measured at any point on this transmission line. Okay, so if we measure the voltage at the end of the transmission line, okay, let's say at this position, or name this position, sorry, by 0. Okay, the end of the transmission line is z equal to 0, so this voltage represents the voltage across the load. Okay, and also if we measure the current at this position, this current represents the current which will pass through the load, so the ratio between them will represent the impedance of the load. Okay, the impedance of the load. But the transmission line itself, without any generator and without any termination, its impedance equal to Z node, characteristic impedance, and this represents the ratio between traveled voltage to the traveled current or reflected voltage to the reflected current. So this is constant depending on the parameters of the transmission line, like its resistance, its capacitance, its inductance, and we calculated previously in the previous parts. Okay, so now if we need to measure how much reflected, how much power, or how much voltage or current will be reflected in this system. Note, now I call this as a system because we have generator or transmitter, transmission line, and load. So in such system, if we need to measure or calculate the reflection, okay, we can do that by measuring or calculated many parameters. Okay, we will start with one of them, which is called voltage reflection coefficient, or for more simplicity, reflection coefficient. Okay, because sometimes we use a current to measure this reflection, or sometimes we use the power to measure or calculate this reflection coefficient. So the first parameter which will be calculated or measured, okay, to give us a knowledge about how much reflection along the system, this parameter is reflection coefficient. Now if we need to calculate or if we need to define the reflection coefficient, we could say the reflection coefficient represents the ratio between the reflected voltage to the traveled voltage. Okay, reflected voltage, this is specifically voltage reflection coefficient. So reflection coefficient represents the ratio between the travel to the the reflected to the traveled. Okay, and this ratio could be derived from the relation between the Z load and Z node. We know the impedance at the load represents the ratio between the voltage at the load or across the load and the current which pass or which could be passed through the load. Okay, and any one of them represent the superimposition between the traveled and the reflected, also the current traveled and reflected. So from this value we could, from the Z load defined, or the ratio of the Z load, or the definition of the Z load, we could derive a relation between Z load and Z node. Okay, and then we could use this relation to derive the value of the reflection or the voltage reflection coefficient. Okay, if we normalize the impedance, the load impedance, if it's normalized to characteristic impedance, that means is divided to the characteristic impedance, we could simplify the relation to be normalized load impedance minus 1, normalized load impedance, ratio between normalized load impedance minus 1 to the normalized load impedance plus 1. Okay, this is the reflection or voltage reflection coefficient, and is dimensionless quantity. And remember, if we need to calculate the power, we need to square this value. Okay, because power proportional to the square voltage, and if we need to calculate it for the current, we need to give this quantity opposite sign, the minus, and we will see that next. So the reflection coefficient is a vector quantity. It has amount or magnitude and phase. Magnitude represents the absolute magnitude, the absolute ratio between the reflected to the traveled, and phase represents the delay between, or the phase difference between, the traveled and reflected. So if we need to calculate the reflection coefficient, we need to calculate it as a magnitude and phase. The value of the reflection coefficient is always confined, or it's between 0 and 1. So the minimum value of the reflection is equal 0 of the reflection coefficient is equal 0. That means there is no any reflection. That means Z load is equal to the Z node, and there is a perfect matching between the load and the transmission line, and according to that, all the power which travels through the transmission line will be delivered or dropped at the load, and there is no any reflection part. Okay, more general case, transmission line with a characteristic impedance terminated by load with an arbitrary impedance. Okay, So according to that, the magnitude of the reflection coefficient is depend on the value of or values of z load and z node, and also its phase or phase difference of the reflection coefficient. It will depend on this value. But in case of the transmission line is terminated by a load, its impedance matching with the impedance of the characteristic. Okay, so there will be no reflection, all the power will be delivered. If this transmission line is the worst case, okay, maybe here we have worst cases. If the transmission line is terminated by a short or by open circuit, so all the power will be reflected. So according to that, the reflection coefficient is equal 1, all the voltage will be or current will be reflected. So the maximum value of the reflected or the maximum magnitude of the voltage reflection coefficient is 1, okay, and the minimum is 0, okay. Difference here between the short and open is the phase difference. So the voltage here will be reflected totally by phase difference equal 118 degree, okay. So we could say the value of the reflection coefficient, the total value here, -1. But in case of open circuit, if the transmission line is terminated by the open circuit, so the power or the voltage will be reflected in phase with the traveled, okay. This is the most important, and also we have other special cases, like when the transmission line is terminated by inductance or transmission line is terminated by capacitance. The reflection coefficient magnitude is also 1, but this amount will be affected by the phase, which is depend on the value of the reactance part at the load and the reactance part at the Z node, or the reactance part at the load and the characteristic impedance, whole characteristic impedance. Here with this animation we have transmission line with a characteristic impedance equal 50 ohm, okay, and there is an electrical signal, okay, applied on this transmission line, okay, and this transmission line is terminated by short circuit, so its impedance equal to 0 ohm. So it's terminated by short circuit, and we expect all the power or all the voltage or the current will be reflected, okay, in phase with the out of phase with the traveled one. This is regard the voltage, and in phase regard the current, okay, no problem. So the green wave represent the traveled, and the gray one represent the reflected, and the blue one represent the superimposition between them. So if we focus on the wave in blue, we could see the wave is a station, okay, so is standing. There is no any transferring in this wave. It's look like confined between this point and this point, and just move up down up down up down. So it's called standing wave or stationary wave, okay. Same for the current case, of course, with the difference in the phase 90 degree. So the traveled in green, the reflected in gray, and the superimposition in red here. And we could see the red wave is standing, okay, just move down up down up down up. So according to that, there is no any transferring to the power from the generator to the load. All the power will keep confined where in the transmission line, okay, between the generator and the load. And this is very bad issue, okay, because we need to send this information or this power or this signal to a certain load, for example to an antenna, to convert this electrical signal to electromagnetic and radiate it, okay, in a free space. But now there is no any power delivered by the antenna, okay, So no any power will be radiated as an electromagnetic wave, and all the power keep confined along the transmission line because the standing wave, or confined as a standing wave because the reflection. Okay, so this is the reflection effect of the transmission line. Is very bad effect. Okay, so again, the reflection coefficient represents the ratio between voltage or reflected voltage to the traveled voltage, and in case of calculated by the current, we need to opposite the sign of the reflection coefficient, and in case of it's calculated by the power, we need to square the value of the reflection coefficient. Okay, because the ratio or the relation between the power and the voltage proportional to the square voltage. Power is equal to the voltage square multiplied by R resistance. In this example, we have a transmission line with characteristic impedance equal 100 ohm, is terminated by a load, and this load consisting of resistance with 50 ohm in series with a capacitance with 10 picofarad. Okay, so we need to find the reflection coefficient of this system. Okay, so we have characteristic impedance is equal to 100 ohm. This is for transmission line. Okay, and here we have a load with an impedance is equal 50 minus 10 picofarad. Okay, of course the electrical signal which will be applied in this system operates with 100 megahertz. Let's first, according to this relation, find the normalize the impedance of the load to the characteristic impedance by dividing the impedance of the load to the characteristic impedance. So that's what happened here, and the normalize will be equal 0.5 minus J 1.59 ohm. Okay, that's good. This is the normalized, and we could apply the formula of the reflection coefficient here. Normalized minus 1, normalized plus 1. Okay, and then we will get the reflection coefficient as a magnitude and as a phase. So as a magnitude, there will be 0.76 from the traveled voltage will be reflected. Okay, the phase between the reflected to the traveled will be about minus 60 degree, 0.7 minus 60.7 degree. Okay, this is the phase between the traveled and the reflected. Okay, thank you very much.